Hello everyone. In this video, we are going to do an example of vector subtraction. Um, and the reason for that is because vector subtraction is fairly identical to vector addition, just with one additional step. Um, and that additional step is taking the negative of the vector that you want to subtract. Okay. Um, yeah, so we're given this equation. We have some VR, which is going to be what we're trying to find, what we're trying to calculate, and that's going to be found by subtracting V1 from V2. And that means that we'll need to take the negative of V1. Um, and so to see how this is fairly identical to vector addition, I find it useful to write this equation as V2 plus the negative of V1. Um, and getting that negative is really where vector addition differs from vector subtraction. Okay, since we have our equation, I also find it very helpful to plot our vectors just to get a sense of what everything looks like and what our resultant vector will look like. Okay, we have V1 is 3 and 8. So let's say this is 1, 2, 3, 4, 5, 6, 2, 4, 6, and then 2, maybe we can go 2, 4, 6, 8, and same thing down here, and same thing over here. And that'll be our 6. Okay. And those need to be negative. And since we go up to 8, I'm going to do every other here, just so that we have enough space. Okay, yeah, so with the vectors, they write them exactly the same as you do points on a Cartesian grid. So we have V1 equals 3 and 8. And so what that represents is like the x component of V1, which we can write as V1x, and that equals 3, and the y component of V1. And that is 8. So just like with a Cartesian point, you have the x and the y. So we have our x component is 3, so that'll be somewhere around here. Let me draw this in a different color. It'll be 3 up to 8. So our V1 is going to be from the origin. Vectors are always from the origin. Like that. That's going to be our V1. And our V2 is minus 1, 4. So we go x is minus 1, up 4. So this is going to be our V2. Like that. That's going to be our V2. Okay, yeah, so that's what our V1 and our V2 look like. Now, we need to take the negative of V1. And the way that we do that is we flip the direction on both the x and the y components. And so flipping the direction just means we change the sign of them. So because we have 3, 8, we change the sign on the 3. That would become minus 3. And 8 would become minus 8. And just as another example of taking the negative, for V2, if we wanted to take the negative of that, which we don't in this case, this is just another example, the negative 1, we would flip the sign on that, so it would become 1. And then for the 4, we would flip the sign on that, and that would become negative 4. But that's just another example. Uh, we don't actually need that for this problem. Okay, we can also graph negative v. So this is negative v1, and that's going to be minus 3, so that'll be over here, and down 8. So it'll be something like this. And you can see that the direction is exactly opposite of what v1 was. So this is negative v1. Yeah, the direction is exactly opposite, but the length still stays the same. So when you take the negative of a vector, only the direction changes. Okay, now we can take a look at what will happen if we add v2 and negative v1. So let me draw this uh, on a separate plot just to make things a bit clearer. And I always like to sort of follow the order of the equation. So when we're adding vectors, we add them tip to tail. So we can add, we go from like the tip of one vector, and we move the tail of one vector to that location and add them tip to tail. And so like I was saying, I like to follow the order of the equation. So we can use v2 as our starting point, and then add negative v1 to the tip of v2. So if this is our v2, I'm just going to quickly draw it without numbers or anything, just so that we can do this a bit quicker. Then negative v1 will be down to the right like this, actually something like this. And so if this is our that's our v2, this is negative v1, and we can use a different color for our resultant vector, which is going to go from the origin to the end of our vector addition. So that's going to be our VR, our resultant vector. Okay, now how do we calculate where the endpoint of VR is? Well, to do that, all we do is we add the x components of the vectors that we're adding and the y components of the vectors that we're adding. So the way that I like to write this is, maybe we can color code this, VRX equals, and then we'll have V2X, and we're adding V1, or sorry, we're adding minus V1X. And so if we take a look at the values that we have, V2X is negative 1. So we can sub that in, negative 1. And we're adding V1X, that's negative 3, plus negative 3. And so if we add those together, that'll become negative 4. And we can do the same thing for the y's. We would have VRY, equals V2Y plus minus V1Y. And if we sub in our values again, V2Y is 4. And we're adding negative V1Y, which is negative 8. So that would be plus negative 8. And if we do that, that gives us negative 4 as well. So the endpoint of this vector here, where VR ends, and also where V2 plus negative v1 ends, because those are equivalent, is negative 4, negative 4. That's that point there. Okay, and that is our answer. That is v2 minus v1, or v2 plus negative v1. All right, thank you for watching.